In this video, we are going to be discussing gas chromatography, a specific type of column chromatography in which the mobile phase is just an inert gas. We are also going to be discussing the effect of temperature on elution time and the concept of temperature programming. In our previous examples of column chromatography, we talked about the fact that the number of equilibria are based on the interaction of a compound with the stationary phase and the mobile phase, its relative solubilities in those two immiscible phases. In gas chromatography, we are not interested in the interaction of the molecule with the mobile phase, because in this particular case, the mobile phase is just an inert gas. The retention time of the compound therefore has more to do with the vapor pressure or the volatility of the compound. A more volatile compound will spend more of its time in the vapor phase and therefore be moved down the column quicker. This means that the adjusted retention time or the partition ratio is actually going to be inversely proportional to the vapor pressure. Remember that the retention time is how much affinity it has for the stationary phase. So as we increase the vapor pressure, then we decrease the retention time. The volatility of a compound comes from the equilibrium set up by the Clausius-Clapeyron equation, where the vapor pressure is going to be a negative delta H of vaporization, a constant for the molecule, divided by RT plus C. If you remember from general chemistry, it is a logarithmic relationship between the intermolecular interactions and the temperature. This can give rise to the fact that that means that instead of being the negative logarithm, the logarithm of the retention time is going to be equal to some constant for the molecule, whatever that may be, divided by the temperature plus a constant, where the retention time can be calculated if you know certain constants. Now, this constant is going to lump together the delta H of vaporization of that compound, the ideal gas constant, the length of the column, the flow rate. This is going to be a column-specific constant, as is this. But each column, each compound will have specific constants. So, if we have a compound that has an adjusted retention time of 21 minutes at 200 Cs and 13 minutes at 225 Cs, what temperature will be required to elute the compound in 10 minutes? Okay, this data seems to make sense because as we increase the temperature, we decrease the retention time. So clearly we're going to have to increase the temperature higher than 225 in order to get it to elute in a faster time period. But we can use this equation to calculate it. From this equation, the ln of 21.3 is equal to whatever constant that is, divided by 473 Kelvin. This is the point at which I want to remind you, of course, that all of your gas calculations have to be done in Kelvin. So you have to convert between Celsius and Kelvin by adding 273. So we have that equation, and we also know that the ln of 13.3 is equal to B over 498 plus C. Look, we have two equations and two unknowns. Algebra ensues here, and we can solve for this constant and this constant by simultaneous solutions of those two equations. From that, we get a B of 4,428 and an intercept of minus 6.305 if we push it to a ludicrous number of significant figures. From those two knowns, we have now got those two constants, and that means we can write this equation as ln of any retention time is 4428 over the temperature plus a negative 6.305. If we just substitute in the temperature works out to be 515 Kelvin or 241 C.